Hello, my name is Dr. Taheri, and this would be a tutorial on a phase diagram, specifically carbon-iron phase diagram. I've been teaching material science for a number of years, and I have to admit this is one of the most complex topic to be taught. It's hard for professors to teach as well, not because it's hard, but because it's so easy and so natural to me. It's almost like I want to teach you guys how to breathe. It's really no way to teach unless you think about it in a very less complex way. We talk about the inverse lever law, and students sometimes ask, why inverse? Sometimes they are not sure about how they can use that. Let me give you an example. Okay, if I want to give a metaphor, have you guys look at those stereogram? So those random dots, and you just kind of focus, and then after you crossing your eyes, a picture comes out and say, wow, here is a Ferrari, I can see it. And then you want to explain to someone, do you see the Ferrari? And the guy said, what? I said, well, look at that, here's the rim, here is the hood. And the guy said, are you crazy? It's really, you have to get to the point of, I would say, epiphany, and then say, that's it, that's all it was about. This is truly true for when you're using the calculation phase diagram. So let me start by talking about the inverse lever law. So why we call it inverse? People are asking, so why is inverse? And let me give you an example. So imagine that you're here in Vernon and you want to go to Kelowna. That's a good example. So, and assuming that we will measure the closeness to Kelowna between 0 to 1. If you are too far, the furthest you are in Vernon, you haven't even moved, we call it you are 0% close to Kelowna. If you are in Kelowna, it's completely full 1, which is 100%. So, someone called you again from in Kelowna, asks you, where are you? So, well, I'm at home in Vernon. I'm not even, came to that point. So, I will call you later. So then you come here and imagine this distance is 48 kilometers. So you go and travel 16 kilometers, 1/3, and the person calls you again. How close are you to Kelowna? And what you do, the math is you do this length, which is 16, divided by the entire distance, which is 48, and that's 0.33 or 33%. So you said, I'm 33% close to Kelowna. That's exactly the inverse lever law. This to the whole thing. You go further down, and now you are at 32 kilometers from the Vernon, and the person again called, how close are you to Kelowna? And then you do again inverse lever law. You do this length, which is 32, divided by the entire length, which is 48, and it said I'm 66% close to Kelowna. That is truly as much as complex as it gets when it comes to calculation of phase diagram. Absolutely. I again mentioned in my lectures, so the math here is like a grade 4. It is very, very basic. But application of that could be, I have to admit, could be confusing, and especially these things should be collaborated with laboratories. You have to look under the microscope, you have to check things, and then it become more clear. So let's start with the most basic example in phase diagram. So you have a phase diagram, it has two elements, whatever, let's say copper and nickel. I call it XA and XP. So this on x-axis is the composition of your situation, of your system. So if you are here, you have 0% of B, 100% A. If you are at this point, you have 100% B, 0% A. You could be anywhere here, assuming you are in X sub 0 at the temperature T. So you are a two-phase region. In this region, you have solid in equilibrium with the liquid. You always have to be identified at any point two things. One is how many phases do you have? What is the equilibrium? Here you have one phase liquid. Here you have one phase solid. In this region you have two phases, solid and liquid. The second thing is you have to identify the composition of liquid and solid. What is inside the liquid and solid? So obviously at any temperature you have 2 points here. This gives you the composition of liquid and this gives you the composition of solid. And then writing the lever law, it's very simple. So imagine I'm X sub 0. In X sub 0 I have two phases, solid and liquid. XS or X sub S is the composition of solid. XL or X sub L is the composition of liquid. The mass fraction, which is the weight percent of solid, is this length inverse, you see from Vernon. So this length to the entire length. This is X sub 0 minus XL divided by XS to XL, the entire length. And in the same token, the mass fraction of liquid, how many percent liquid you have, which is, by the way, 1 minus the percentage of, or 100 minus the percentage, if you talk about the percentage of solid. So it's equal to this length, S sub S minus X dot, divided by X sub S minus X sub L. And needless to say, if I add these two together, so if I add them together, so what I get is, obviously, I write it here, X L divided by X divided by XS minus XL plus, so X sub S minus X sub 0 divided by XS minus XL. So obviously you can write down here, this becomes X sub S minus X sub L and X minus XL plus XS minus X sub 0. The answer is going to be XS minus XL divided by XS minus XL, which is 1. That's obvious. So the math is very basic. So it could be anywhere. It could be here, further down here. If you go further this direction to my, in this side, so you will have obviously a longer solid arm, so the amount of solid become more until you get to this point, which is 100% solid. If I go to this direction, the amount of liquid become more until I get to this point, which is 100% liquid. So this is as far as the inverse lever law is concerned. So you want to calculate this weight percent, you go and do the inverse arm. So I hope this part is clear, and then we extend this to the next level, which is eutectic or eutectoid phase transformation. Now let's talk about the eutectic phase transformation. Eutectic phase transformation is when you have one liquid, unified liquid, it transforms after reducing the temperature to a certain degree, all of a sudden to two solids. the equation is L become S1 plus S2. And this is a general form of eutectic phase transformation, which when you understand the eutectic, you can understand easily eutectoid. Pretty much the same concept. So we have few regions here. We have 1, 2, 3, 4, 5, 6 regions. This area is liquid. Liquid contains A and B. A and B are elements. This again is the percentage of one of these two elements. If I have, let's say for example, 30% A, obviously I have 70% B. So this is the composition of my system. So alpha is a solid solution containing lots of A, a little B. Beta is a solid solution containing lots of B, a little A. So these are these two. And whenever you cross this line, which is the eutectic line, whatever liquid you have in a system, it forms to two solids, alpha and beta. So this is in the form of lamellar structures, layer by layer, zebra shape. That's the definition, and that's the way that they come under the microscope after you etch it. So there are few things that you have to understand in this diagram. First of all, anything, and by the way, if I'm right at this point, at this composition, which I'll call it XE, at the eutectic or eutectoid, in this case eutectic, at eutectic composition, I have 100% liquid. So truly 100% liquid become 100% eutectic, zebra shape, alpha and beta. But not necessarily I'm always at this particular composition. I am less or more. If I'm less than the eutectic composition, it's called hypoeutectic composition. If I'm above or more than the eutectic composition, it's called hyper. Again, remember hypothermia, hyperthermia. Hypothermia means it's the lack of heat. Hypothermia means heat exhaustion. Okay, so obviously if I am, and one more thing, anything above the eutectic is called pro or pre. We also call it prime as a phase. So if I break this one in 4 quadrants, so in this region I am in pro, means before, so pro hypoeutectic. In this area I am pro hypereutectic. In this area I am in hypoeutectic. And this area I am in hypereutectic. That's one thing. We have to be able to identify the composition of each phase and the number of the phases exist at each temperature and composition, any X or Y. Assuming I'm at this region, starting from here, 100% liquid I have. Maybe I just zoom out. So I have 100% liquid, so we call it 0.1. So the structure I have here is 100% liquid. I mean, anyways, liquid doesn't have a structure, but assuming it looks like this, because there's no grain boundary, there's no boundary. So as soon as I come to this point, call it 0.2, I have a very small grains of alpha is forming, and they would be forming at the grain boundary, because this is again is true for eutectoid. So assuming that there are regions, preferred regions, so these are the small grains of solid. And as I coming down here in 0.3, for example, so remember the previous example. So here I have solid and liquid in equilibrium. If I want to know how much solid I have, how many percentage, I go this arm divided by the entire arm. This would be the concentration or the composition of liquid, and this would be the composition or concentration of solid. So therefore, at point 3, I get more of this grains of solid. Up to this point, at this very point, I have maximum possible amount of my solid in equilibrium with liquid, and for this case is this much divided by the entire arm. So this becomes larger. So these are my solids forms in the structures. So what do I have the remaining? Is liquid. I know exactly how many percent it is. This tiny, this region divided by the entire one, assuming this is correct. So what happens right after I move to this transformation? So all the solid I have form that zebra shape. So the solid will turn all of a sudden to, looks like this. The liquid forms all of a sudden to this shape. All my liquid will be formed that zebra shape which solidify, and this would be my final structures. So now the question is, at this point, right below, slightly below the eutectic temperature, what are my system composition? So the composition of obviously solid alpha is always this much. The composition of solid beta is always this much. And the composition of liquid is this much. Okay? So these are all given. I can simply write the inverse lever law for just above the eutectic. I calculate how many percent of solid before eutectic I had, which is called pro-eutectic solid or primary solid, and then I can say the remaining is liquid, and liquid become two solids, alpha and beta. So the math is at this point here, so if this is my concentration of x sub 0, and this point is x alpha, and this point is a eutectoid, or eutectic in this case, composition, the weight percent, right here, the weight percent of my alpha primary is equal to this length, maybe I should magnify it, this length to the entire length, this length to the entire arm, and that is equal to x eutectic minus my composition x sub 0 divided by x eutectic minus x alpha. So this is the amount of solid. 1 minus this is equal to the amount of liquid. So I write it here. So that would be obviously x 0 minus x alpha divided by xe minus x alpha. You add them together again, become 1. So this term is already the solid. It does not participate in phase transformation. The only currency we have is the liquid. Liquid goes to two phases. One phase is alpha, one phase is beta. But let's see, how does it goes to two phases? In that case, I have to write the inverse lever law at the Eutectoid tick. And at Eutectoid, I have 3 points. This point, and this point. So no matter how much liquid I have, always liquid would be goes to these two forms of solids, alpha and beta, with the exact same composition, because this is depends on this particular case. In any kind of eutectic, you have copper and nickel. All these numbers are given by nature. So let's see how it goes. So I write the inverse lever law. So once at the point I wrote, and this is, for example, the mass fraction or the weight percent of alpha eutectic is this, again, inverse. I want alpha, I go to beta. This divided by the whole thing. And that is equal to x beta minus xe divided by x beta minus x alpha. Amount of the beta, weight percent, beta eutectic, is equal to 1 minus this, which is obviously equal to xe minus x alpha, x beta minus x alpha. Again, you add them together, the total value would be 1. So this is, in any case, I have 1% liquid or I have 99% liquid. But in this particular case, we realize that for this x sub 0, this is amount of my liquid. So therefore, from this many percentage liquid I have, let's call it 30%. This many percent become alpha, let's call it 40%. And 1 minus 40, let's call it 60%, become beta. So as an example, if this value become 40%, and this value is also 40%, and this value is obviously 60%, and this value is a 60%, and maybe just for make it not same number, I change this one to actually 70 and 30. So 70% and 30%. I have 30% liquid. So now, if I want to write the entire situation, see what I have 70% or 0.7 of my alpha prime, plus I have 30% liquid, of which 40% become eutectic alpha. So it's going to be 30% of 40%, this become alpha eutectic, plus 30% of 60%, this become beta eutectic. In total, I have 70% alpha primary, plus I have 12%, right, 0.2, just to be consistent, eutectic alpha, plus 0.18 beta eutectic. So in total, it's 100% is 1. It has to be. Now, if someone asks you, wait a minute, how much of total alpha you have, regardless of alpha in the eutectic or solid alpha, you add these two values. So you add these two values, and the values would be 82% of alpha general, and you have 18% of beta general. So that's exactly what we have. In this case, I have two kinds of alpha, primary alpha and eutectic alpha. I have one kind of beta, eutectic beta, at this. Exact same thing is true when I am on the other side, which is called hyper-eutectic. Except the fact that in hyper-eutectic, I have two kinds of beta. I have primary beta and I have eutectic beta. I have one kind of alpha, which is eutectic alpha. So this is truly all it is. So no matter how you do it, you might ask, oh, wait a minute, so how do I calculate, without going through this, if I want to get the total amount of alpha at below the eutectic, how do I do it? Then you write the inverse lever law below the eutectic. And the calculation is, again, it's very easy. So what you do is, you are at this x sub 0, you want to know how much alpha you have. Is this, forget about the eutectic now, is this length divided by the entire length. And I think I should maybe write it here in this area. So this would be total weight percent of alpha. I have to go a little lower. So the total alpha weight percent, or weight percent of alpha, either way. Weight percent of alpha. So that is equal to the inverse lever law, which is this guy. So imagine this value and this value, we talk about it. It's equal to x beta minus x sub 0, x beta minus x alpha. If I want to write the total amount of beta, which is one kind of beta, which is the eutectic beta, the value would be simply x sub 0 minus x alpha divided by x beta minus x alpha, and then you add them together, become 1. So this is totally as far as you think about both case scenario. By the way, mathematically, if I want to know the total amount of alpha, which is here, I can do this. I can parametrically, I multiply this. So I keep this value and I multiply this value, this liquid, by this value, which is the weight percent of the liquid, and the answer will be the same thing too. So you have this is the primary, plus this multiplied by this term, plus this multiplied by this should be exactly the same thing. So you might say, why I don't use a simple form? You could. But sometimes you are not interested in total amount of alpha. You want to know how much primary alpha you have and how much eutectic alpha you have. And more interesting is, in real practice, well, we do all these things. I mean, you can buy a $2 million microscope and you do like a EDS, energy specific spectrometry, and then you can measure what is the percentage of each. But if you don't have that $2 million machine, this shaft broke, you go and cut it and you just go polish it and etch it, look at microscope, and you look at what is the actual, by image, what is the weight percent, because surface represent the weight, because mostly they have the same kind of density. So you see up to 30% of this solid primary. From there you can guess actually the alloying element in this. So this simple calculation could replace a $2 million machine in a very basic way. So for example, in carbon iron, you look at that and look at the amount of primary alpha you have, and by knowing how much primary alpha you have, you can simply go and calculate, with a good approximation, calculate the carbon content of this alloy. So therefore, not always you're interested to know in total how much alpha you have. Most interested, how much primary phase you have. From the primary phase, you can go and calculate what was the composition. Okay, here is the phase diagram of carbon iron. It's kind of a schematic. We have to identify few areas here. First of all, we have to remember some numbers here. Here 0.022, which is the amount of carbon can be dissolved in iron in a form of ferrite. BCC is 0.022%. Then on the other side of the spectrum, we have the maximum amount of carbon can be dissolved in iron, which is cementite, is 6.67. Some books says 6.7. And then it's the eutectoid carbon content, 0.76%. This is the eutectoid phase transformation, in which I write here solid 1 become solid 2 plus 3. That's the eutectoid. We have another phase transformation right here, in which we have a liquid become two solids. That's the eutectic. So we have liquid become solid 1 plus solid 2. So these are the two major phase transformation here. We have one here is very small area, which unfortunately I don't think you can see the top there. That's protectic phase transformation. One of the characteristics of the eutectic, as we mentioned in the class, is we have the lowest melting point. In this phase diagram, if someone asks you, show me the lowest melting point, means you go anywhere here and find an area or point that you have liquid and what's the lowest temperature. Obviously here is the point. You can see that here, and that's 1147. Iron melts in around 1500, but you can add 4.3% carbon and you have a eutectic composition at which iron can melt around 1200. And that's very desirable because you don't have to take it another 300 degree to melt the iron. So I really encourage students to try to completely visualize and try to be able to draw this phase diagram. It's very schematic. And then, the more importantly, we need to actually be able to write lever law in different areas. We know that the carbon content below 0.76 is called hypoeutectoid. Above that is hypereutectoid. At 0.76 is called eutectoid composition. So first of all, let's talk about the eutectoid phase transformation in carbon iron. We have austenite. FCC. It forms ferrite plus cementite. We know the carbon content of ferrite, no matter how much you have, is 0.022% carbon. We know that the carbon content of cementite is 6.67%, which is the maximum amount of carbon can be dissolved in iron. And we know that austenite at the eutectoid temperature right at this point has 0.76. So first of all, I want to know how many percent of my final structure as a weight percent is ferrite and how many percent is cementite. I need to do the inverse lever law, and I deal with three simple points. The points are one point here 1 point here, and 1 point right there. So if I want to write the inverse lever law, maybe I erase this part, or I don't even need that. I write it here. Hopefully we can see. I would say the weight percent of ferrite eutectic is equal to, is equal to this length. Talk about inverse lever rule. This length divided by the entire length. So that is 6.67 minus 0.76 divided by 6.67 minus 0.022, and this value roughly is around 889, or let's just simply say that it's 89 or 89%. So, not carbon, 89%. This is the mass fraction, weight percent. So, this is the amount of weight percent of ferrite in perlite, right here. I write, let me delete here now just to make it a little easier. So I want to do the exact same thing for amount of cementite, and I could write obviously 100 minus this or 1 minus the other one, but I just write it down here. The amount of cementite eutectoid is equal to 0.76 minus 0.022 divided by 6.67 minus 0.022, and this value is roughly around 10.89, or it's roughly around 11%. It just would be roughly around 11%, or 11%. So this would be roughly around 11.01. Oh, we don't care about lucky write down. It's like 11%. So that means in my structure of perlite, I have 11% cementite and 89% ferrite. Let's just do a kind of reverse calculation. I want to know what is the carbon content of my perlite. Perlite carbon content. Okay, I have 11% of cementite and it has 6.67%, and then I have and I think you can see it there, yeah, and I have 89% of ferrite, and you add them this, I guarantee the value becomes 0.76, and there is no coincidence, because if this is the child, the mother of this is austenite, and austenite has the same amount of carbon content. Obviously, the carbon does not fly or vaporize, stays in the system. It just goes to two different constituencies, one with higher carbon, one with lower carbon. And the structure, obviously, in a perlite is like this. So it's kind of like a lamellar structure. So it is lamellar structures, which is like this. So we have different clusters of zebra shape. So each of these, they have layer by layer, ferrite one layer, cementite one layer. If I magnify that, it looks like one layer of ferrite, and then you have two tiny layers of cementite. So obviously, I don't know how well you can see that here, atoms of carbon would migrate out of the ferrite because originally it was 0.76. They have to migrate out to deprive this ferrite from carbon, and of course they go to the neighboring layers, and this they will have more carbon, 6.67 and 6.67. So that's how it is. Okay. When you look at the microstructure under the optical microscope, I mentioned many times, you see dark white. Students often say, oh, the dark one is carbon. That's not true. This is optical microscope. First of all, if you polish the surface and look at the microscope, you will see nothing. You see some superficial scratches. You have to etch the sample. Etch means you introduce a mild acid, and that mild acid actually brings up the grain boundary. The phases with more grain boundary, obviously, they look darker. What phase has more grain boundary? Perlite. If you see a bright white phase, that could be either additional ferrite or primary ferrite or primary cementite. That's the math, everything around here. And that's happened exactly at the eutectoid carbon content. Now, imagine I'm not at eutectoid carbon content, either I am in hypo or in hyper. For that reason, I would have primary ferrite or primary cementite. So I would delete this part and then I deal with both cases here. Assuming I am in hypoeutectoid, means my carbon content is less than 0.76%. Let's say I have roughly around 0.39% carbon. Okay, so I'm somewhere around here. Maybe I make it as a kind of here. So this carbon content is 0.39% carbon. Let's see what do my structures. So at this point I have austenite. At right this line I start to get ferrite. At each point I go, I have some ferrite, go down, more ferrite. The maximum amount of primary ferrite forms at exactly 727. So I'm right at this point, and I write the lever law. So there are 3 points here. One is 0.39, 1 point is 0.76, and one is 0.022. Let's see, for this case, how much would be my actual primary phase. So I write here the weight percent of primary ferrite. So it's equal to inverse lever law. So this length divided by the entire length. That length is 0.76 minus 0.39 divided by the entire length, which is 0.76 minus 0.022. Ironically, this becomes 0.5. Means 50% is primary ferrite. How much is the austenite? I can write then is going to be another 50%, but just for double checking. So is this length minus the entire length? So that is 0.39 minus 0.022 divided by 0.76 minus 0.022, and this is going to be 50% or 50%. So it will be 0.05 or 50%. So my structure is 50% of, maybe I do it here like this. So it's going to be 50% white blobs of ferrite, and the remaining 50% it's going to be perlite. So here so these, the pink one that you see, assuming is perlite, the white one with no grain boundary, they are ferrite. I can do again the reverse and see if this is correct, just to prove that I'm in the correct carbon content. Let's see how much carbon content this has. In a sense, assuming I don't know it has 0.35% carbon. I saw that under the optical microscope, 50% ferrite and 50% perlite. I do the math here. The carbon content of my phase, is equal to, so 50% ferrite plus 50% of 50% of ferrite plus 50% of perlite, and perlite has 0.076, and this value it ended up to be exactly what I got at the beginning. You can break this term also down to two terms. You can maybe make it larger. So you can say that, okay, 50% is perlite, right? What is inside the perlite? Inside the perlite is 89% ferrite and 11% cementite. And I guarantee this is pretty much the same as this. So you can calculate the carbon content of the alloy knowing the microstructure. So that is the case that is called Eutectoid. Bear in mind, if I reduce the carbon content, let's say my carbon content instead of 0.39 is 0.19, means I'm gonna go toward this side. And it means the arm of the primary ferrite is gonna be increased. Look at this here now. This term becomes less. This term is constant. Then I get more primary phase. And that makes complete sense because in total I have less carbon. The phase with less carbon has to be increased to compensate for the entire carbon content of the alloy. As I go this direction, I have less carbon content, more primary phase, which is a ferrite. So this could be said also from the other side. I do another math here on the hyper, and I will compare these two together. Now, assuming I am in a hyper eutectoid, so I'm just somewhere around, I would say maybe here. And my carbon content is 0.35% carbon. I'm in a hyper eutectoid. Let's just draw first of all the structure. The structure looks like this. So you have colonies of perlite and you have white strips of cementite. So these guys are cementite. And these guys are perlite. By the way, the perlite, don't forget, is 89% ferrite, 11% cementite. So in this case, I have two kinds of cementite. I have primary cementite, I have eutectoid cementite, which is exactly the opposite of the other side. I have primary ferrite and eutectoid ferrite. Let's just do the actual math and see how many percent I have primary cementite and how many percent I have the perlite. So again, I do the lever law just above the eutectoid point. So I have 3 points, this point, and this point. So if I want to know how much cementite I have, primary is this length to the whole length. So I write here, so cementite primary, the weight percent of it is equal to, it should be equal to, the carbon content was 1.35. So it's going to be 1.35 minus 0.76 divided by 6.67 minus 0.76. This to the whole thing. And this value would be 0.1 or 10%. Let's do the other one. See how much is my eutectoid phase. So the weight percent of my eutectoid phase is equal to how much austenite I have, because austenite will form perlite, is this length to this length. So it's going to be 6.67 minus 1.35 divided by 6.67 minus 0.76, and I guarantee this is 0.9 or 90%. 90% are those blobs of the zebra shape, which looks dark under the optical microscope. Let's do the reverse. I want to know, assuming I see this structure in my microscope and I don't know what is the carbon content of this alloy, I simply write, okay, the weight percent, the carbon weight percent, or the carbon content of alloy is, let me just go lower here. So weight percent of carbon is equal to, just do it like this. So I have obviously 90% of my austenite, which become perlite, so it's 0.9 multiplied by 0.76 plus 0.1, 10% I have cementite, and this value become 1.3. And if you like, you can break this one down to again 89% of ferrite plus 11% of cementite. That's exactly looks the same. So I end up to have the same. By the way, now if I increase the carbon content, means going this direction, going this way. By increasing carbon content, this arm is going to be larger. That means the amount of my primary phase, which is cementite, is going to be more. And that again makes sense, because if I have more carbon content, I have to have more weight percent of the phase with more carbon. That's exactly the opposite what we said regarding a high eutectoid. In high eutectoid, by decreasing the carbon, the phase with less carbon become increased, which is primary phase. In hyper, by increasing the carbon, the phase with more carbon, which is primary phase, is going to be increased. The question that we talk about in the class is, what is the carbon content of that alloy that by decreasing the carbon content to 1/2, the primary phase mass fraction double? So you have to put this from like a context, word by word, to the material science terminology. So obviously, if I'm in hyper and I remain in hyper by decreasing the carbon content, the cementite, which is the primary phase's mass fraction, decreases, not increases, because cementite has more carbon. I must be in hypoeutectoid. So, assuming that I am in this line and I don't know my carbon content. The carbon content is C sub 0, unknown. So the question says the mass fraction of primary phase, but let me calculate that to the weight percent of the primary ferrite, which is in this case here is this length, which is C sub this length, which is 0.76 minus C sub 0 is 0.76 minus C sub 0 divided by 0.76 minus 0.022. This is the mass fraction when you have C sub 0. This amount doubles when I reduce the carbon content to 1/2. In the second case, so primary ferrite, so I have 0.76, this is C sub 0 divided by 2, 0.76 minus 0.022. So this value, let's call it, I don't know, prime. So this value is twice as this value. So I write just a simple equation here. I put this twice as this. So if I write it here, maybe it's easier. So 0.76 minus C sub 0 divided by 0.76 minus 0.022. Twice as this is equal to 0.76 minus C sub. This is equal to, let me just, don't need this here now. C sub divided by 0.76 minus 0.022. So this cancel this, twice as this. So it's 1.52 minus C sub 0 is equal to 0.76 minus C sub 0 divided by 2. You simplify that and 0.76 is equal to, sorry, this is 2 here. So bring it the other side, is going to be 3 C sub 0 divided by 2. From here, so C sub 0 is equal to 1.52 divided by 3. And this is 1.52 divided by 3. Okay, the answer is, oops, 0.507. That's the carbon content of my alloy. Oh, you want to do a little bit of kind of reverse the numbers. Let's see what is the carbon. So let's say what is the primary phase in this. The primary phase in this is this divided by the whole thing. So the answer here, if I want to find the primary phase here in this guy, in this guy. So obviously is the value is, I write it here, 0.76 minus 0.7 divided by 0.76 minus 0.022. So this answer is 0.76 minus 0. That's about 34%. Yeah, we can see it here. It's about 34%. So let me just... this is 34%. I have 34%, oh, not carbon, sorry. 34% primary ferrite. How about here? So, well, let's just do the math here. Same thing, 0.76, 0.50 divided by 2, 0.76 minus 0.022, and this answer is 0.76 minus perfect. The answer is roughly around 0.68 or 68%. You see that I reduced the carbon content by 50%, half, and then the primary phase double. Now, here it is easy. Is this question have another answer? Is there another scenario? Yes. So if you read that question, it says that what is the carbon content of an alloy in which by reducing the carbon content to half, the amount of primary phase doubles? It doesn't say what primary phase, it doesn't say same primary phase. So obviously, I know with a high level of confidence that I cannot be in hyper and ends up in hyper. But what if I'm in hyper, when I make my carbon content half, I cross over and I end up to be in hypo. That is completely a different scenario. Now, here is the case that I'm in hyper, I reduce it by half the carbon content, I become hypo. I write in a hyper, assuming I'm here, so what is the primary phase? Primary phase is this guy divided by the whole thing. So here is the weight percent of primary cementite, I'm in hyper, is equal to unknown value, I don't know how much is that, C sub 0 minus 0.76, and is 6.67 minus 0.76. That's whatever value is this. And I end up to be in hypo. In hypo, I have ferrite. So primary ferrite, that is this length. So it's 0.76 minus C sub 0 divided by 2, 0.76 minus 0.022. This is twice as the other one. So all I need to do, I just maybe simplify this. Here is so this becomes C sub 0 minus 0.76 divided by 5.91, and here is 0.76 minus C sub 0 divided by 2. In a sense, I can affect the 2 here just to make it this become 1.52 minus C sub 0 divided by 0.76 minus 0.22 multiplied by 2, 1.476. Okay, so this value is twice as this. So I write down here C sub 0 minus 0.76 divided by 5.91 multiplied by 2 is equal to 1.52 minus C sub 0 divided by 0.76. So I just simply go here and 5.91 divided by 2, so it's C, yeah, I can say C minus 0.76 divided by 2.955 is equal to 1.52 minus C sub 0 divided by 1.476. And I simply simplify that. This so here simplify, and I think we can see it. Yes, so it's going to be C sub 0 minus 0.76 is equal to 2 roughly multiplied by do a little bit of simplification here. So you go here, so C sub, yeah, I can see still is equal to 2 multiplied by 1.52. Let me just see if I did any mistake here. I'm just going to double check the calculation. So this is correct. So 2C, okay, cancel this one, C, multiply by 2, multiply by 2, and then you divide them, and that is correct. So just want to make sure it's correct. So then this is equal to, I just got it here, 2 multiplied by 1.52 minus 2 multiplied by 1.52 plus 0.76 divided by 3, and the answer is correct. 2.7. This is the carbon weight percent. Let's do the math here one more time, see if this is correct. I mean, the number is correct, but I want to see if this works out. If I have 1.27% carbon, let me calculate how much is my primary cementite. This is the value here. So I just simplify this. So it's going to be this value minus 0.76 divided by 6.67 minus 0.76. And I have roughly around 8.5% cementite. Primary cementite. This is my initial carbon content. I reduce the carbon content to half. What is the half of this? 1.27 divided by 2. Now I have 0.635% carbon. Let's plug it on this guy here. See what is my the carbon content of my primary ferrite. So I write it here. So it's going to be 0.76 minus 0.635 divided by 0.76 minus 0.22. Perfect. That is 17% carbon. Wow. I reduce the carbon content from 1.27 to half, which is 0.635, and I increase my primary phase twice. Used to be 8.5% and now it's 17%. Bear in mind, this primary phase is cementite, those are rivers. This primary phase is ferrite, blobs, but the question didn't say that. So this question has two answers. Either you are in hypo, remaining hypo, or you are in hyper and you cross to the hypo. This answer, whatever you find, somehow half of this should be less than 0.76% in order to be correct. If ever the half of this is more than 0.76, the answer is there is no answer for this question. because you have to cross. This is the material science representation of that. Now, the question was asking, what is the carbon content of an alloy which by increasing the carbon content by 2 folds, the primary phase reduces to half, exactly the opposite. So you increases the carbon content twice, and the primary phase decreases by 2 folds. So in that case, so either you are here, you go from here to here, or you are here, you go from here to here. So you can play around. And if I ask the question, what is the carbon content of an alloy in which, by reducing the carbon content to half, the percentage of primary phase remains the same, is only one answer. It has to cross. There's no other solution. Because if I'm in hypo, staying hypo, or if I'm hyper, staying hyper, it cannot remain the same. The only scenario that by increasing or reducing the carbon content to twice or half, primary phase percentage, mass fraction remains the same is I cross the line. So this, if you can understand that and follow this, most probably you will have no problem in this chapter. Bear in mind, this value here, 0.76, it's only when you have carbon iron. If you talk about if you have alloying elements, all of them reduce this percentage. If you have 4% nickel, instead of 0.76, you have 0.7. That's one thing. So everything is shifted this side. As far as the temperature is concerned, if you add alloying elements, there are 2 categories. The one category is a chromium family, one category is nickel family. The nickel family is actually caused the reduction of the eutectoid temperature. So it stabilizes or promote austenite. In a sense, even at room temperature, I'm glad I didn't break it, so even at room temperature, you can get austenite, like austenitic stainless steel. The other side, if you add chromium stabilizers or chromium family, then that actually promote formation of ferrite. They are ferrite stabilizers, they're promoting ferrite. So it means this 727 will be shifted up, this region is going to be expanded or contracted in the other case. So there are lots to observe here, I have to admit. Students sometimes, they have problem to understand it. But go over this, review it, and most probably you will have a better understanding of the phase diagram. I hope this, I guess 1.5 hour or whatever long is lecture helps you. Thank you and have a wonderful time.